Hello everyone, thank you for joining us today. On behalf of Saint-Gobain Technical Insulation, welcome to this webinar, Designing Cold Insulation Systems with Elastomeric Foam. For your information, this webinar will be recorded and shared through our social media. Let me introduce myself. I'm Anna CAPIT, and I work in Marketing and Communications in the Technical Insulation Business Unit. I will be introducing this webinar and our speaker in just a few moments. But before we start, I'd like to remind you that you can ask us all your questions in the live chat during all the events, and that you can also ask questions anonymously. The Q&A button is on the right-hand side of your screen. We'll take some time at the end to answer these questions. Next slide, please. To briefly introduce Saint-Gobain Technical Insulation, we can talk about the different markets in which it operates. Since 1937, we've been providing sustainable insulation solutions to customers in all technical markets, such as industry, marine and offshore, HVAC, and different OEM markets, like automotive or household appliances. Next, please. We are present worldwide through our two international brands, HUEVET and Kaimann, as well as a certain number of local brands. Our strength is that we're not only global, but also local, as we have dedicated teams in many countries and regions of the world. That allows us to be close to our customers. Next, please. We offer insulation solutions made of different insulation materials. The HUEVET brand stands for mineral wool solutions, both glass wool and stone wool. These solutions are mainly dedicated to applications at temperatures above ambient, which can go up to very high temperatures, like 700 degrees Celsius. Through our Kaimann brand, we offer solutions based on elastomeric foam, which are dedicated mainly to cold applications, below ambient temperature, where condensation risk can be observed. And this brings us straight to the heart of today's webinar topic. Next, please. Let me introduce our speaker, who will guide you through the topic, Designing Cold Insulation Systems with Elastomeric Foam. Malte HUEVET is the segment manager for HVAC and part of the international Kaimann team. Overall, Malte is responsible for the HVAC product portfolio. This includes managing new product development projects, from idea to market launch, as well as providing support throughout the product lifecycle. He will be today's speaker, as he is an expert in his field. So Malte, the floor is yours.
Thank you very much, Anna, for the introduction. So I will talk today a little bit about the world of elastomeric foam and give you a brief overview about the general topic, cold insulation system, how they should be designed and how they should get installed. So for this, we split it up, this webinar, into 5 sections. At first, I want to give you a short introduction. So why are there in general cold insulation systems necessary? Then for the second part, we will dive into the topic of elastomeric foam. What kind of elastomeric foams are there available and what are its properties? Then for the third part, I will show you some application areas and give you some ideas and examples where you can use elastomeric foams. And then for the most interesting part, I think so, for the fourth and fifth part, I will show you how to design an elastomeric insulation system, and especially because I think you learn from its best if you made already maybe some mistakes. I will show you some mistakes that happened from customers in the past and how not to design and install an elastomeric system. So let's start with the first chapter. Why are effective cold insulation systems so important? So at first, in general, we use or need a special insulation system for every situation where we got the medium temperature below the ambient temperature. There we got always the problem that there could occur condensation. So that means also we need something that has a built-in vapor barrier and where we can make sure that the water and especially the condensation will stay outside the insulation. Our biggest enemy, of course, is always the corrosion under insulation, and especially if you got a cold system where you are using operation temperatures below the ambient temperature, then we are always concerned and got the risk that there could condensation water occur. So just to give you an idea, for example, in Germany, I think we had in the last year around 2 billion euros of annually damage to buildings just by water leakages, by bursted pipes, and of course they are mainly caused by corrosion under insulation. So in this way, the best solution is to prevent this kind of damages already before they could occur. And for this, we need also, of course, a suitable insulation system, which is properly installed. And of course, especially regarding the minimum insulation thickness, correct designed. Before I will start about elastomeric foam and in general, I want to bring you a little bit closer the basics of thermodynamics and creating and designing the correct insulation system. So for this, at first, there's three different types of heat transfer. At first, we get the convection. This is the absorption and dissipation of heat by a fluid. So in this case, on the right, in the picture, we can see there's a liquid, it's water, it's boiling, and there happens an exchange of the molecules, of the water molecules itself, just by convection through the flowing fluid. So this flowing fluid can be, for example, also the pure air, and there happens mainly the exchange of heat through the convection. Then we got also the conduction. That's always that there are two different types of body with a different temperature and contact, and because of the laws of thermodynamics, the bodies want to be always in an even state. So this is also the reason if you touch, for example, a metal surface, why the metal surface feels always cold, because the heat goes always from the hot side to the cold side, and both bodies wants to be in an even state regarding the temperature. Then for the third, we get the radiation. This is mainly the heat transfer through electromagnetic waves. So for example, if you are outdoor, the sunlight is mainly caused, or the heat of the sun is mainly caused by the UV light of the sun. And this is the radiation, and this is also the third type of heat transfer. Then if we talk about condensation and the dew point in general, so our air contains always a certain amount of water. This is always defined by the humidity, and it's always connected to a certain temperature. So air can only contain, limited by its temperature, an absolute amount of water. For example, if we got a cubic meter volume of air, and the temperature of the air is 5 degrees, then it can contain around 7 grams of absolute amount of water. If we would raise the temperature, for example, up to 30 degrees, then this air can already contain around 30 grams of water. So this shows already the right graph where we can see for this situation, we had at 14 degrees, for example, a relative humidity of 100%. And if we would raise the temperature to 18 degrees, then we would have only 70% relative humidity if the absolute water in the air will stay the same. If we will drop below the 100% relative humidity mark, then we reached already the dew point, and the dew point is a point where the air is completely saturated, so the air can't keep up any more water, and that's also the point where the water will start out on surfaces, for example, which are colder than the dew point. So the dew point in general can be mentioned like this, that there is a constant condensation and evaporation, and in this point, exactly at the dew point, we are in balance of this constant condensation and evaporation of the gas-moist mixture. So what you should keep in mind for the following slides. If we got warmer air, then it can contain always more water vapor in comparison to cold air. If we decrease the temperature below the dew point, then the air is saturated and the water will start fall out. So, and that's also the point where we will see that the condensation starts. How does it look in a real case scenario? So in this case, for example, a bathroom, we got a very high temperature so around 25 to 30 degrees, and a very high humidity with 70 to 80%. And we got two uninsulated pipes without any protection. What will happen there if we got a medium temperature, for example, of water with 5 degrees? The warm humid air will cool down around the pipe through the convection of the air around it, and also it's also a little bit caused by the radiation. And after the air cooled down and dropped below the dew point, we will start that the water falls out of the air, and there will occur condensation on the pipe itself. And this will cause and end up after a while, of course, in corrosion and so on. So what kind of insulation do we need to prevent this problem? So especially if we want insulation for prevention of condensation, of course, we need at first the good thermal conductivity of the insulation material, and we need the right insulation thickness. These both are mainly relevant to bring the dew point up from the surface inside the insulation. We want to have always the dew point inside the insulation, not on top of the pipe and not on the insulation itself. And we need a material, of course, which has a built-in vapor barrier. So, for example, elastomeric foam has a water vapor diffusion resistance of 10,000 mu. That's a unitless value. And this is also known as the safe value, so where we are already talking about built-in vapor barrier, so there's no aluminum foil, anything else needed. Then what's the thermal conductivity? Thermal conductivity in general represents the heat flow through a 1 cubic meter of volume of a body when the temperature difference is 1 Kelvin. This can be a drop or a raise of the temperature. It always depends, of course, where the warm side is and where the cold side is. What you always should keep in mind that the thermal conductivity of a material is always related to a specific temperature. So for a cold insulation, it's normally always connected to 0 degree. For warm insulation, it's normally always given to 40 degree. If we also have a very big difference in temperatures, for example, if you get an insulation which should be used at, for example, minus 200 degree, then you should also keep in mind that the temperature, or with the temperature, the thermal conductivity of the insulation material will change also. So, for example, at 0 degree, we got maybe 0.33 watts per square meter Kelvin, and for example, at minus 50 or minus 100 degree, it can be already at 0.2, for example. That should be also taken into account, because that's also the reason why there's always a formula given in the technical data sheet, and then we should calculate the thermal conductivity always related to the point and to the temperature. Then what's the water vapor diffusion resistance? So the diffusion in general is the movement of the gas molecules through a liquid or solid. Or the solid can be, for example, also our building material or insulation material. And related to the water vapor diffusion resistance, of course, is the movement of the water molecules through a building material. Why is it happening? So it's always connected to the laws of thermodynamics, and because the water molecules in this case want to go through the material, because the partial pressure is different inside the room in comparison around the insulation or around the pipe below the insulation. And so because this different pressures wants to be always in an even state, that's the reason why the water molecules are always going through the material and wants to be in balance. So after I gave you about the basic knowledge, a short overview, I will start now with a part of elastomeric foam and its properties. So an elastomeric foam, or also called flexible elastomeric foam in general, is a plastic material that has a certain shape and behaves in general elastically. So you can tweeze it, you can twist it, you can bend it. It will always go back to its original shape. This original shape has been given during its manufacturing process, so it's called cross-linking of the rubber polymers, or also vulcanization. Maybe you know it sometimes from car tires, for example. It's also the same process. And at this point, the material itself gets its elastic properties and also its dimensional stability. So that's the point where the rubber can't be reformed. The rubber polymers in general come from the nature, for example, from the gum tree. That's then called latex. And the most technical rubber foams or rubbers in general are mostly made out of synthetic rubber, and that's produced out of mineral oil through chemical processes. So this is the view on a chemical basis on some different products. So in comparison, for example, FEF and the polyurethane, they are from its chemical structure very similar, but also different. So the one on the left, the elastomeric foam, is very flexible, while the Duroplast, of course, is very stiff and brittle. But what have they common is that they got both a chemical bonding. So you can see it with the dots inside its structure. In comparison, a polyethylene foam, for example, there's just a physical bonding. That means also you can always remelt a polyethylene foam and give a polyethylene foam, for example, or polyethylene in general, a new shape. While with an elastomeric foam or a Duroplast, like in polyurethane, it's not possible. How do we create a good thermal performance with an insulation material made out of FEF? So at first, we need to create very closed and fine cells. So like we learned in the beginning, if the cells would be bigger and open, then we would have of course, more convection through the air. Then what's also very important, we need a very even cell distribution through the entire material. So that means also that there are no defects, of course. That could happen sometimes, for example, if there are rubber agglomerates that are also defects. That's mainly caused by unexposed propellant, for example. And these rubber agglomerates, so that's mainly a rubber bulb, you can say, so an unexposed part of rubber compound inside the foam. And of course, because it's a solid piece of rubber, they form thermal bridges. So that's always what we want to avoid and what we don't want to have in a thermal or a technical insulation. And what we also need is a very smooth surface. And even inside the cells itself, the surface needs to be as smooth as possible. What different shapes do we get? So at first, after the oven line, our products will always end in the oven line as a standard FEF tube. So without any cutting or anything else. Then we got also, of course, our self-adhesive tubes. This also with an overlapping tape, so for additional secure protection. And we got also pre-covered FEF tubes. The same range is also available for sheets. So we got the standard sheet without any cladding or self-adhesive, then a self-adhesive version, then the version also in endless row, and also pre-covered with some aluminum cladding, for example, or some other cladding. So to sum it up, why is in general a good solution to use an elastomeric foam for cold application areas? So at first we get a so low sensitivity due to its closed cell structure. So every cell is closed by its own, and even if I puncture the insulation, the cell below will always protect the pipe from getting wet or that there could occur even condensation. So then the material itself has also by its own a very high vapor barrier, so that there is no aluminum foil or something similar needed. The rubber itself, or rubber foam in general, is water repellent, and in combination with its closed cell structure, we have the ideal solution, of course, for preventing wetting of the insulation. And in this way, of course, because the insulation can't get wet, we get also no performance loss and no basis for corrosion under the insulation. Also, the rubber foam itself is resistant against corrosion and microbial growth. So it's also the ideal solution for hygienic and critical environments. And because it's very flexible, you can also easily shape molded parts out of it for complex geometries. Now I want to show you some application areas where you can use, or where our customers, for example, are using elastomeric foams. Of course, we got at first, just as a general overview, all the different HVAC parts. So for example, for ducts, for refrigeration pipes, cold water pipes, but also as a connection line for heat pumps, for example, or as a duct insulation. And we got there also for solar heating, there with an EPDM foam. Because this foam is also UV resistant. We got there also prefabricated connection lines for the solar panels with already included stainless steel pipes, and also with wiring to connect all the sensors of the solar panels. Then some more examples for OEMs. Also, some of our customers are inline using our elastomeric foam for pre-insulating, for example, shutter boxes, so that they can already include the stripes of elastomeric foam directly in their production line. Then also for the housing or for the internal components of a heat pump, for example, or also for automotive, like battery electrical vehicles, so for the cooling systems and cooling components, and also what is also a common version or use case, a do-it-yourself camper solution. So this is a solution how one of our customers using it inside their heat pumps. We are already producing prefabricated and pre-cutted parts right from their DXF files, like the customer sent it to us. And we made it out of a self-adhesive cladded product, so that the customer just has to remove the release liner. In this case, it's a condenser where the self-adhesive sheet parts are already pre-cutted, and it has to be just put around the condenser, and there has to be not to be used any sharp knives or solvent-based glues or something similar inside their production line. So in this way, of course, it's a very simple, easy and clean solution. Then we got also applications for the industry. So a lot of our customers are using, for example, our materials or elastomeric foam for very cold going pipes down to -80, -20 degree with a multi-layer construction. So for the first layers there, we need always the EPDM, then to protect the material while it's shrinking against each other from rubbing with an aluminum foil covered. And then when we reach a temperature above -50 degree, then we can go to our normal material, the MBR PVC material. These are mainly customers out of the pharma or food industry. And we got also some multi-layer structures for noise reduction solution available. You can see it in the picture in the left corner below. There is at first the closed cell elastomeric foam used, and then a heavy mass layer, for example, and then on top our Kaimann, that's an open porous material, and that is, for example, a solution which is also tested after the 15665 ISO. We got also halogen-free solutions available for critical requirements, like, for example, on some cruise ship projects. In this case, there was a requirement that it should be easily cleanable. So they added also on top an aluminum cladding. And there was, of course, also the requirement to be compliant with the solar requirement. And this is all fulfilled, for example, from our K-Flex HF pluses too. So after we got now all the basics, I want to show you the most interesting part, I think so how to design and install elastomeric foam. So for everybody who's not familiar with insulation in general, for example, in Germany, it's a normal profession job. So you have to learn at least for 3 years until you can call yourself as an insulator. And I tried to split it up into 4 different parts for everybody who's not familiar with insulating in general. And so for the first part, of course, we have to choose the right insulation, especially related to its environmental conditions. We got the different materials. I will explain you on the following slide. Then we need to calculate the minimum insulation thickness if we want to create just a system which is protected against condensation. But especially in today's time, with high energy prices and high electricity costs, we should always take into account that it makes maybe sense to look for the optimal insulation thickness and compare the minimum insulation thickness also regarding energy savings with the optimal insulation thickness, we can call it. And then for the last step, of course, we have to install the insulation according to our guidelines and rules and norms. So what kind of insulation materials from elastomeric foam are there available? So our standard products are always based on MBR PVC. They got a very big temperature range and very good thermal performances. They are available with BS2D0 class for tubes and BS3D0 class regarding its fire behavior for sheets. So, and this is really the standard product which is used in the most cases in normal houses and all the HVAC segments and so on. Then we got our EPDM material. This is mainly used for areas where you got a very big change in temperature. For example, if you got, for example, pipe, which is normally always with a medium temperature around -10, -20 degree, for example, or close to 0 degree, and you need to flush it with hot steam, with high pressure, for example, then you can use this kind of material because it's very good for changing temperatures, but also for a big temperature range. Also, this is the only material which is UV resistant. All the other materials has to be protected at least after 1 day. Then we got also our halogen-free solution, so the pure nitrile-butadiene rubber. This is mainly made where the smoke has to be as low as possible toxic. So like in marine or rail applications, so everywhere where you can't run away or run into freedom. For example, on a marine ship, you can just close all the shots and then burn it down, but you can't run away or jump off the cruise ship, and that's the main reason why there's always the requirement that it needs to be halogen free. Then for the last product group, we got the chloroprene rubber types. So they got also very good thermal performances, and they got also the property that they smoke as low as possible, or that the smoke that gets produced by their products in a case of fire is as low as possible. And for example, there's also a version with sheets with BS1D0 available, and also for tubes, of course. And these are mainly used for escape groups. So then for the next part, we need to calculate at first, of course, the minimum insulation thickness. So like I mentioned before, the target is always that we set the dew point inside the insulation. We don't want to have it on the pipe itself, and we don't want to have it on top of the insulation, because otherwise the insulation will get starting wetting, and also that it drops everything down. Therefore, we got the different calculation standards, so the ISO 12241, the VDI norm, and the ASTM. But if you don't want to calculate by the formulas by your own, then you can use, for example, also our pre-calculated tables. We got the guidelines available, where we pre-calculated all the different insulation thicknesses, the minimum insulation thicknesses related to different relative humidities and room temperatures, and of course also related to the different medium temperatures and pipe diameters. So this is one option. Or if you want to calculate it by your own, for example, with the formulas of the VDI, then you need at first always a minimum medium temperature, then the heat transfer coefficient of the outer surface, so that's mainly connected to the convection and the radiation of the surface. And for example, an FEF has a value of 0.93. Then you need also the information about the airflow in general, if it's an outdoor application, indoor application, if there's maybe a wind speed, if you apply it outside, and so on. And we need, of course, the maximum temperature of the environment and, of course, also the relative humidity. So if you don't want to use all the different formulas from the VDI, for example, then you can do it also in an easy way. We got there a free and online available calculation tool. That's our KaiCalc. And there are plenty of options available. So you can not only calculate the minimum insulation thickness with this tool, you can also calculate, for example, the freezing time of a pipe if there's a standstill. You can also compare different insulation materials, also you can compare different thicknesses for all the different kind of shapes, so like tanks or tubes, ducts, with all the different materials and also different orientations. So this is also one option. And what we can or what we should do in today's time, especially related to the high energy costs, we should also make a comparison between the different insulation thicknesses, because in this case, for example, what I've done there on the right side, that's a report from KaiCalc. It was a DN 125 pipe with a medium temperature of 2 degrees. It was just a 10-meter long pipe and a system that was running for 1 year and an ambient temperature of 25 degrees and 70% humidity. So, and in this case, the minimum insulation thickness was just 30 millimeter. There we dropped already in our operational cost from 690 euros per year to 179 euros per year. But if we would add, for example, additional 12 millimeter insulation thickness, then we drop even below the 179, of course, and save additional 66 euro per year, and that would result, for example, in a payback time for the thicker insulation version of 2 years. And after this time, of course, we save already 66 euros annually, year by year. And this is calculated, what I forgot to mention, this is calculated just with 9.4 cents. So KaiCalc offers this option also regarding CO2 savings, for example, but especially for calculating the operating times and payback times. This option is also included into KaiCalc. Then we need to calculate also our material consumption. So especially for the bigger diameters of a pipe, for example, how much sheet material do we need to apply, and also how much glue do we need to fix all the joints and seams of the insulation material. Then when we start to install our insulation, okay, what do we need for this? We need at first our application guideline if you aren't completely familiar with insulating at all or insulating with elastomeric foam. Then it's also good to know the basic knowledge about the rules and norms. I will show you on the following slide what we have to take into account while we are insulating with elastomeric foam. And we need some basic tools. So at first the sharp long knife, then a measuring tape, pen and circle for marking all the different shapes on the insulation. And we need a brush or adhesive pump, for example, and of course insulation material and adhesive itself. So regarding insulating with elastomeric foam, what do we have to be concerned about? At first, on the application side, so you need to take into your mind that every open area of the insulation is a potential risk of condensation. So it's not the same with warm insulation. There we would just have some more energy losses at this place. But if we want to install a cold insulation, we must always take into account that if there is an open area where the surface temperature will drop below the dew point, then we will see that there will form water and condensation. So that means also we need to seal every joint, every valve, every pipe support very properly, very tight, and everything needs to be completely sealed. Also, we shouldn't make any big air gaps and also not too much tension. So the risk is there always that we got a V-opened joint, for example, or some seams which can go open. And that's also why we don't want to put the insulation on the pipe with any tension. Regarding the rules and norms, of course, we must calculate the insulation thickness, especially regarding or related to the correct environmental conditions. So that's also the most common mistake, that the expectation of the room are always the same. So there could be maybe an area where there is not that much airflow in general, and then the problems will start because the system itself is maybe from the insulation thickness correctly calculated, but that could be that in some certain areas there is maybe less air circulation, and then you will see, of course, the minimum insulation thickness is not thick enough, and then you will see also that there starts condensation. Then we need to take account also that we should always have at least 100 millimeter space between pipes, ducts, and also to a wall. And for tanks, it's also recommended that we have at least 1 meter of space between it. So what's also very important to take into account if we are working with very low temperature, that the material, because it's a rubber, will of course shrink, and that needs to be calculated also pretty well into the length of the material. Then from the environmental aspects, we should always consider into that we got the right processing temperature. So too hot is not good, but also too cold is not good. We should stay always between 10 to 30 degrees. That's a good temperature for processing. And what's also important for any other material excluding EPDM, we should always apply directly after 1 day of installing the insulation a UV protection. Regarding the adhesive, we should always take the flash off times into account so that we don't stick the material too fast together. We should always make sure that the glue is already dry. So also if it seems like that the glue won't stick anymore, if the glue is dry and you got the right tag of the glue, then you can put the material together. If it's still wet, then you need to wait a little bit longer. Then also the sealing bonding needs to be made on the pipe every 2 meters. So that's especially regarding some damage to the insulation. When a section will get damaged, then the insulation just for the 2 meter part will get wet under the insulation, because of course if there is a ripped off part of the insulation, then there is no insulation anymore and it will start form condensation. But all the other parts are completely safe. Also, we need to apply a full surface bonding for diameters above 600 millimeter. So this is which has been properly installed. So we can see that there are no open joints. Every valves and every pipe supports and so on are completely covered. There's no open area, and we can see that, of course, there's no water on the ground. That's also a good indicator that everything has been sealed properly, and there's also no forming of ice. What you can also see that there's not any glue where it shouldn't be. So a good insulator is always just the glue on the seams and joints, and there hasn't been used a lot of tape just for the parts where we need to use some tape, and that's also a good indication for a good insulated system. So this is now a good example how it shouldn't be applied. So, for example, in the left case, there was used some sheet material. It has been just wrapped around with a lot of tension and fixed all together with some tape. But this system, over a long-term perspective, maybe it works for a short time, but not for a long-term perspective. So then what could happen also with the seams and joints, especially regarding our adhesive? So the adhesive needs always the right processing temperature. If you go below 10 degrees, then you should always make sure that the solvents are really flashed off so that the gluing feels already dry enough until you put the material together. Otherwise, you have to wait a little bit longer. And also on the opposite side, if you are working in very high ambient temperature, then you should try to reduce the ambient temperature by additional ventilation, for example, or if it isn't possible, then you should or could maybe switch also to our EPDM glue. This is a glue which has been especially made for workplaces in higher temperatures, and there is a bigger amount of solids in the solvent, in the adhesive, and this allows us also to have a little longer flash off time. Then also one example of self-adhesive tubes where the tension in the 90-degree band was way too high. So in this case, the solution would be to make some molded parts so that you cut the tube in two parts and glue it again at the joint then together so that the tension on the material is completely gone, and then all the self-adhesive will also stick in a way like it has been designed. So this is a good example how it will look after an insulation will get damaged. Of course, the insulation itself is completely dry, but especially the point where it was punctured or the piece is ripped off, there the insulation itself isn't thick enough to stay above the dew point, and then we will see a situation like that. That in the damaged part there will occur condensation water, and that's also, of course, not what we want to have. So in this way, the solution would be to exchange this part, and also, or what could be also be made is that we re-insulate with the second layer, but there must be also a complete sealed second layer so that it's glued on the first layer of insulation. This is a typical scenario where we won't have, or where we do not have enough space between the pipes and ducts. So you can always compensate with some additional insulation thickness. But of course, if you reduce the space below the 100 millimeter, then you will also reduce with additional insulation thickness, the air circulation between the pipes and ducts. And at some point, you can't bring the humidity in this specific area down, or not down enough, so that you just can improve or solve this problem with adding additional air circulation. And this was for this customer also the solution. This is a good example of how an insulation, if it's not EPDM, will look after 1 year or 2 years in direct sunlight. So the insulation itself will start to get completely brittle and fall into several pieces. And in this case, we also have to exchange the whole insulation because there's also no performance regarding its thermal conductivity more given. And we need to completely re-insulate this system and also add, of course, at least after 1 day, a protective layer of paint or a protective cladding. So to sum it up, why should you choose a Saint-Gobain elastomeric foam solution? So at first, we are best in class regarding our worldwide availability. So I think we are present in every country or close to every country. Then we are also a service partner. If you get any problems regarding your job site or regarding your construction, you can always consult us, ask us for solution. Our technical and application engineers will always try to help you, and will try to find a solution. Then, of course, we can also do with you together some customer trainings if you want to, also on the job site. And we got a long-standing experience regarding elastomeric foam. Our products are all third-party certified and designed for top performance, not only regarding thermal conductivity or thermal performance in general, also especially regarding fire behavior. So, for example, for sheet products, we are the only ones who offer a BS1 D0 solution. There's no competitor available who has a similar solution. And we are delivering also all the additional certification, like for marine or indoor air quality after Eurofins. There are all our products certified after gold standard, for example. Saint-Gobain itself set its approach to sustainable solutions or sustainability in general to a high level, and all our products, or close to all our products, are also EPD certified. And in this way, we are also contributing on a high level to the green building label scheme, so like the DGNB, WELL, LEED, and BREEAM. And our products in general save up to 580 times more than they emit during manufacturing. We ourselves are already producing our elastomeric foam just with green electricity, and Saint-Gobain itself set its goal to be carbon neutral in 2050. So then also, if you are especially a customer regarding OEM or industry projects, we can always start a co-development with you, so that if you got any specific requests regarding packaging or regarding the dimensions or also pre-cuts, feel free to get in contact with us, and we will find a solution with you together. So thank you very much for taking part of our webinar today, and now we will answer your question.
Yes,
Anna.
Yeah, thank you very much for this very clear presentation. As you said, we will now answer some questions from the chat. So we will try to answer the most liked questions first. So if you want, we can start with the first one I have here. That is, does elastomeric foam falls into the scope of new coming PFAS regulation?
Yeah, so all our elastomeric foams are completely produced without any PFAS. So I know it's a very big problem currently, which is especially discussed in the European Union. So I know that they want to want to ban all the PFA group or the whole PFA group, which is covered by 10,000 or thousands of equivalents, but our products in general are completely PFAS free.
Okay, that's very clear. Thank you. I have a second question just here. Do the material is mixed with some chemicals which might be easy addicted to the fire and might be blown up? So I understand this one as, is there any chemicals that are combustibles in the insulation material?
So Most of our products are also or contain also flame retardant. Otherwise, it won't be possible to achieve, for example, a B class with rubber foam. Rubber in general, of course, has the probability that it wants to burn, and in this way, we are with the flame retardant, we are able to achieve the higher classifications. But in general, of course, there will appear smoke, but all our products won't bust any special dust or chemicals into the air.
Okay, so here we have another question. Hi, would you explain the critical thickness of this type of insulation?
The critical thickness of this type of insulation. Though I think this question is related to the minimum insulation thickness. The minimum insulation thickness is always related to the environmental conditions. So, like I mentioned, that's very depending on the medium temperature. And especially on the environment itself. For example, if you get a humidity of 80%, then it could be with a medium temperature and 25-degree ambient temperature. Then it won't be enough to insulate, maybe also with above 25 to 32 millimeters. Then you have to stay even higher. So it's really heavily depending on the humidity especially, but also, of course, on the ambient temperature and on the media temperature.
Okay, sure. Very clear. Thank you very much. I have another question here with 3 likes. Do you have significant difference between regular product and the product for sound?
Yes, so our regular product, which is used for cold insulation application, is a closed cell foam. Our Kaimann, which is just as an open porous material, so it's produced from the scrap of our production and remanufactured to a new product. And this is completely without any vapor barrier. So if you want to build up a vapor barrier for a cold system and in combination with the sound solution, then you have to use always both products, so the closed cell foam and the open cell foam.
Okay. Okay, next question then. I have one just there. Is the material safe to use in plastic pipes or just metal installation?
It's also safe to use in plastic pipes. So if the question is related, for example, to wall breakthroughs, so fire penetration solutions, if you want to go from one room to the other room, there we got also tested and certified solutions available, also with combustible pipes, also plastic pipes.
Okay. I have just one question here that I think I can answer. Will you share this presentation after the meeting? Yes, we will share on our social media and the LinkedIn account. Here we have another one. Does insulation is valid for just pipes or walls or the entire house insulation?
You can use it also for warm application or for the whole house insulation. But in general, it's constructed or designed mainly for, in the first topic, of course, for cold insulation. But of course, we got, for example, there are also products which are especially designed and made for warm insulation for the houses in general. Yeah.
Okay, I have another one there that's a bit long. I'm gonna read it for you. So, is this material insulation can be used under the ground earth for house construction? And what about waterproof? Is higher pressure? How much this material can resist pressure?
So our material in general, if you will put it, for example, as a connection pipe for a probe heat pump or sole heat pump, for example, Then there is also, we got our EPDM material also with some co-extrusion. So that's an additional PE layer on top of the elastomeric foam. But in this way, it can be used also in the ground. You can't put too much pressure, so you shouldn't put it too deep in the ground, not like 10 meters, for example. But in general, it can be used also in the ground with this PE covering foil. But it would be better to protect it, for example, with an external housing like a plastic tube, so like a wastewater pipe, and that you run then the insulation or insulated pipes through this pipe.
Okay. Okay, I have another question here. Are there also endless tube products available?
There are also endless tube products available, so we can deliver to you. So our normal packaging, of course, is always 2 meter, but we have also available endless tubes with 30 millimeters in one box, or we can also deliver especially for OEM customers, for example, the products on big coils, so up to 300 or 400 meters, for example, that you can directly use it in your production line without too much production waste.
Okay, I think we can maybe answer one last question very quickly. Do I need to apply also a pipe protection paint before insulating with elastomeric foam?
So it depends on the country. Normally, we always, especially in Germany, we give the advice that you should also, before insulating, add a protective paint layer after the RGE 151. So that there's given that the paint layer with a special, or for this design paint, has to be at least 160 mu thick. And this can be done also, for example, with our Kaimann system. And normally you should also apply at first a protective paint layer on the pipe, because you never know if the insulation will get damaged. Then the pipe itself won't be caused by any corrosion under insulation, so that there won't occur any problem because of bursted pipes, for example. And in this way you can prevent this problem.
Okay, well, thank you very much for this answer. So I think we're running out of time. If you still have some questions that Malte didn't answer, feel free to just contact him and he will answer as best as he can. Thank you all very much for your participation and attention. And Malte, I'll give you the floor to finish.
Thank you very much also from my side for your participation. If you need any additional information regarding our products, feel free to visit our website. Also feel free to join our newsletter. And if you get any specific questions related to some projects, for example, you can find our contact data on our website, or you can also directly contact me over my mail or LinkedIn account. Thank you very much and have a nice day.